This is Brian Putt. I'm going to do this webinar on risk-based decision making. This is kind of a replay, if you will, of the tools webinar that's being conducted by Probability Management. These are free webinars and they're live. But for those that are unable to participate in the live webinars, I'm going to record one here. Don't think it'll last an hour though. So what you're going to learn in this webinar is how to use the SIPmath toolbar. We're going to, you'll learn how to create a model that includes risk variables, uncertainties if you will. You can test your uncertainty of the arithmetic of uncertainty. You can generate various uncertainties like uniform, normal, discrete, and triangular. We'll do those in the session today. But there's lots of other distributions that are available through the SIPmath toolbar. We'll see how to manage the sequence of uncertainties. This is really important so you can have consistency in your results, so you can have accountability in the results. We're going to generate some management quality graphics to help explain the results. Oftentimes this is where analysts fall down. They're able to do the complex modeling or financial accounting and everything, but unless you can explain it to management and get their buy-in, there's no commitment to action. We're not going to create a time series model. I think there are several time series models out there on the YouTube that I've created. If you look up Brian Putt, you'll see my videos. We can also correlate uncertainties with SIPmath, but we're not going to do that either today. So the risks that we face and the decisions that we make impact our bottom line, whether it be personal bottom line or our company's bottom line. So some of the applications you might think about are cost and schedule risk analysis. So often costs are over budget and schedules are behind. There was an article today about the Australian LNG plants in Western Australia and how all of them are over budget and behind schedule. You may have inventory control problems that you need to address. When should I be ordering product given the lead times? You know, there are some quantitative equations you can use here, but perhaps simulation is better based on the history of your demand and how it comes in. Maybe it's pretty lumpy or seasonal, and this may be an easier way to look at your inventory control. You may have projects where you need to establish the capacity, decide how big to make things, or if you want to expand things, how much to add. So there's capacity decisions that need to be made. Or you may be making a decision whether to do the project at all, and you need to select to get amongst different alternatives. And finally, you may have portfolio problems that you need to decide which projects to proceed with, which to shelve, which to sell, subject to certain constraints such as capital constraints. In all these cases, you have many options. You have to decide which way you're going to go, which path are you going to take. So let's get into the model. Here I have a blank Excel worksheet. And you'll notice that I have the SIPmath modeler tools installed as an add-in. And if you're having trouble getting them into your Excel, you can go look at my YouTube video on how to install SIPmath toolbar. The SIPmath toolbar has a number of icons. One is to initialize. We're not going to talk about the library. We will talk about the generate input and define outputs. And we'll talk about graphs. Probably won't talk about any of the others either here, but this will give you the basics to get you started. Okay, I'll tell you what I'm going to do. I'm going to come over here and I'm going to show my tabs. That way these will stay up here all the time. The first thing we want to do is to initialize our model. So we'll hit the initialize model, and what's going to happen is you're going to see some new worksheets coming in down here. And we can specify the number of simulations. We'll just use the default of 1,000, but that could be changed later after we build the model. We'll say OK. So here are the worksheets that were added. One's called PM table. That's going to contain a data table that SIPmath will manage for us. And then there's also the SIPmath chart data, which is also going to be managed for us by the SIPmath toolbar. So now we're ready to create some uncertainties. Let's generate some really simple ones just to get started here. And the first one I want to do is a uniform. I'm going to call it uniform 1. And I'm going to put the results here. There's going to be a name that I'm going to give it. This is actually going to be a vector name, but we'll call it there. And so we'll come over here to results and we'll say generate input. Now in generate input, you'll see that there's many different distributions from uniform. Several here are exponential. There's a discrete one that I really like, log normal. Meyerson allows you to specify a P10, 50, and 90, and then it generates a continuous distribution fitting those 3 data points. The normal distribution, well known, Poisson. Resample will resample strings of data, and then the triangular distribution. So right now we're going to do a uniform, something simple. And so it wants the distribution is going to be stored in this cell, C3. Oh, we have a starting ID. We need to talk about seeds. So we're going to put the seed right here. We'll come back and label that. So when you generate random numbers, you typically have some sort of seed. In Crystal Ball or at risk, I believe you're only given 1 seed if you even want to specify one. But here in SIPmath, we get to specify a seed for every random variable. So we'll specify something here in F3. We'll put a number in there in a moment. And we have a choice to type random numbers. We can use rand here, which would be just the Excel rand function, equals rand, open parens, end parens. The issue with the rand function is that it is always giving you a new set of answers, new set of series of random numbers. You have no control over that. So if you ran it one time and got one answer, and then you want to go back and look at the same situation, you'd get a slightly different answer. If you use this HDR, standing for Hubbard Decision Research, then you're always going to consistently get the same series of random numbers. They'll be uniform, okay, but they'll be consistent each time you run the model. So we'll do that one. And then I said we're going to put a seed over here, and we'll use a seed of 10 just to have it. This can be any number you want. You see, if I put in 11, I get a different answer because it's a different series of uniforms. This represents right now only one simulation of 1,000. Okay. Now let's give this a name. I will call it D_uniform 1. Now this is my naming convention, not required, but I like to put a D in front of the name to indicate that it's a distribution. It's not a scalar. Typically oftentimes you use range names in models, but they represent a scalar. This is going to be a vector, and it's going to be a vector of 1,000 outcomes. Okay? So here's the results. And so we will now define outputs. When I define an output, I need to give it a name. That's what I'm going to use here. The output cell is C3, and then we can generate spark lines. You almost have to see these to understand what they are. They're a little histogram of the distribution. We can put these other places, but I typically put them right in the cell for the results. That way I know that it's been defined as an output. And I'll make this a little bit bigger so you can see what it looks like. So here is the uniform. You can see it's a distribution. So now I'll tell you what, let's do that one more time. We'll do uniform 2, okay? And we'll call this seed, we'll do this as 13 just to be different. Okay, I make these yellow because I like yellow for inputs. And over here we'll do this generate input, a uniform, and we're going to specify this is a seed, and we'll say OK. We now have two uniforms. I don't even have to give this a name, but what I want to do here is I want to do the sum of these two uniforms, so it's equal to this uniform plus this uniform. Now we will give that a name. We'll call that sum. All right. Now, so we'll define outputs, output name. We'll get the spark lines, and we now have a distribution. What is that distribution going to look like? You can cheat by looking. You're right, it's a triangular distribution. Let's plot those. So we're going to graph this sum. So I got my cursor on the sum, and I'm going to graph. I'm going to put a histogram here, and I'm going to put a cumulative distribution chart here. So by using the graphs icon here, we were able to generate both this histogram and this cumulative distribution function. We could change this the range here on this axis, because we know that you take two uniforms that couldn't go above 2, so we can have a nice chart there. And so if you're not used to cumulative distribution functions, let me draw this down a little bit. The points here represent the probability, so 60% chance of getting this value or less. So we might call that 1.1. Actually, we could probably come over here and we could get the point. It's 1.08. So there's a 59% chance of getting 1.084 or less, okay? And so there's a 100% chance of getting 2 or less, which we can understand. And the distribution here on this histogram is reflective of the slope of this cumulative distribution function. So that's how you can read this cumulative distribution function. I'm very biased towards using them in doing economic analysis, and we'll see why in a moment here. So let's go down and do another distribution. Let's do a normal distribution here. And for the normal, we're going to need we need a result, we need a name, we're going to need a mean, and we'll need a standard deviation, and we'll have our seed over here. Okay, so let's do a mean of 3 and a standard deviation of 3. And there is a reason why I want to use those values. That'll become apparent as we move on here. So we need a seed, so we'll just put 100 here. Alright, so for this result, we're going to go over to input, generate inputs, and we're going to come down here to normal. And so for the normal, we're going to specify the mean. So I'll point to the mean. Then I'll hit the tab key, which moves me to the next field over here. I'll hit the standard deviation, tab, and I'll point to the seed. Use the HDR again. So now I've got a normal distribution. Let's give that a name, D underscore. We don't have to give these names if we don't want to record. We just want to use them in subsequent calculations. But I want to show you what the normal looks like. So we'll define that as an output and give it a name, and then I can graph that. I'm just going to do the cumulative here. Well, let's see, I guess we'll do them both because people familiar with the normal distribution, so you can see what that looks like. Alright, so here's the normal distribution, and we can see on the cumulative does a really better job of characterizing it, that I've got a mean of here 2.9. Now, is it really 2.9? We could change these decimals over here. Let me show you what you can do. Over here in the SIPmath chart data, each one of these distributions, graphs that we've generated, has generated a column of data where there's information on the histogram data, data required to generate the histogram, and then data required for the cumulative distribution. And in both cases, I can specify how many decimals I want. So in this case, it specified 1 for the normal, but why don't we specify 2? And so we can see the average is really 2.91 with that particular series. And by changing that, okay, I can come back over here to my model, and now these titles have changed. I have more accuracy. Let's try changing a different seed here, 101. So it's coming out a little bit short. Let's do something different. If we not happy with the results, why don't we change the number of simulations? Right now we had 1,000. Let's go over and initialize this for 10,000. I'm going to go over here to initialize, and I'm just going to add 10 here. And when I say OK, it's going to resimulate this, but using 10,000 simulations, and we'll see if this comes out better. So it's better at 2.98, still a little bit short. Now let's demonstrate another distribution. I want to do this as a discrete distribution. Okay. For this discrete distribution, I want to use the values of 0, 0.5, and 1. So these are the values. And then I need to assign probabilities for these. And let's assign probabilities of 40%, 35%, and 25%. Okay? And then I need a place for the cumulatives. And actually the SIPmath toolbar is going to fill these in. So these are the inputs only, along with the seed, and we'll put in a 150 here just to have a number. Okay? Alright, so I come up here to my toolbar, generate inputs, and we're doing a discrete. Here's the discrete. So we'll specify the values. We'll tab, specify the probabilities, and then it wants a cumulative probability. This has to be the same shape as the probabilities, so we'll identify it here, tab, and then we'll go over to the seed and use the HDR. And now I've generated a random variable here that's either going to take on a value of 0, 0.5, or 1. We'll give that a name. We'll call that d_discrete. Okay, and we don't even need to give it a name. I'll tell you what, we're just going to delete that, because what I really want to do here now is I want to multiply this discrete times the normal. So we're going to do normal times discrete. So this is I'm building a model. Here I got my result, and it's equal to the normal. Where's my normal result? Oh, here's my normal result, times the discrete. Did I get this all in the wrong column? Oh my goodness, I'm sorry about that. Let's just take all of this and just move it all over, because I'm going to move it over here. I like to be consistent. So now this normal time discrete is taking column C times the column C. That makes more sense. Let's give this a name of d_normal discrete. Okay, now I'll tell you what, we're going to put a little time sign in there so we know we're multiplying the two together. I think I can actually put spaces, and I'll show you what will happen with spaces in there. So here we'll go to define outputs, and we'll define this output. And it says one or more of the output names has an invalid character. This is probably a space in this case, and SIPmath can convert the invalid names to valid ranges by replacing the invalid with an underscore, and we'll say yes to that. So we now have this value measure, which is defined by, over here on the PM table, you'll see if you look up here, it's put an underscore here where we had spaces. and here are the results. So let's plot that one, and let's just do the cumulative chart here now. So what are we looking at here? There was a 40% chance that I didn't see the normal distribution. Think of these probabilities as, think of the NPV curve as one where I'm thinking about acquiring a company or doing a project, and I'm trying to negotiate an interest in it. And there's a 40% chance I'll be unsuccessful in getting any interest in the project, a 35% chance I could get half, and a 25% chance I could buy the whole thing. So what is my distribution of possible outcomes before I've actually started the negotiations? And it looks like this, and it has a value of 1.3. So there's a 40% chance here that I don't get anything. And then this normal curve, I've actually taken two normal curves and added them together probabilistically at a weight of 35% half and 25% full. So now what I'd like to do is I'd like to demonstrate how I can compare alternatives. So what I'd like to do is compare this curve here to the normal. I want to put the normal curve on top of this. So how do we do that? I'm going to select the graph. I'm going to go up here to design. Oh, I got to do something first. I'm going to come over here to chart data. Don't have to do this, but it makes it easier. Now, we didn't talk about this, but on this chart data, we do have one column for each variable that we've asked for a chart on. And this goes way, way down. And the cumulative data is on the very bottom. To simplify this, I'm going to hit the 1, this is an outline mode. And it basically collapsed all that data, so it wasn't shown. And then I can expand the cumulative here. And so now I just have the cumulative data right below. You'll see how easy that makes in adding to this chart. Take this chart, design, select data. We want to add a curve. And what do we want to add? Well, we want to add this normal times, no, we want to do the normal, don't we? Normal. So if we use the third series name, and we use the x values are the normal values here, and we want the y's are the probabilities, we say OK, we can see here is the full normal curve. Oh, we need a legend over here, so let's get a legend. So we'll come over here and get a legend. We'll put a chart title as well. Now I'll extend this over here. So we have the normal curve at 2.98 and the result before actually starting the negotiation as an expected value of 1.3. And we can see that we can compare those two. Why does this have less downside? Well, some of the time, 40% of the time, I'm not going to see the downside because I don't get the project, and 35% of the time I only see half the downside. So that's why this blue line doesn't extend further down. Same argument for why the blue line, which is multiplying the two together, doesn't have quite as much upside. All right, let's move on to another distribution. This is my favorite. This is called a triangular distribution. Triangular. So we'll have our result here, our name, and for this one we need a minimum, a most likely, and a maximum. So most likely is not the mean, it's just the most likely, the one with the highest frequency, if you will. So then I need my seed. And on this one I also have to specify a random number, or have a place for it to put a random number. We'll see how that works out. For this minimum, I want to use a value of minus 4.5, a most likely a 3, and a maximum of 10.5. Oops, 10.5. And you'll see why here in a moment. And we need to give it a seed. We'll call this 200. Alright, over here in my result, SIPmath toolbar, generate input. We generate a triangular this time. And we're going to specify here the minimum, tab, the most likely, tab, the maximum, tab. Here it wants the random cell, so I'll give it this empty cell to use. And it needs the starting seed. Give it that. Say OK. I now have a triangular distribution here. So let me give this a name, D underscore triangular. Remember, I don't always have to give names to everything. But in this case, I want to be able to compare this triangular distribution to the normal curve. So I do need to do that. We'll define outputs, specify the name here, say OK. I guess I need to generate the triangular, I need to generate a cumulative distribution function here. So I'm going to do that. I'll put that here. What that did was to generate the data I need for the cumulative distribution function. So now I'm going to take this chart, I'm going to copy it and take it over here because I'm going to modify this chart. Just going to put it right up here, and then I'm going to I get the chart, switch off the chart. And then I have my chart up here, hopefully. Yeah, there's our chart. Now what I want to do is I want to change from this normal discrete. I want to take this blue line and make it the triangular. Swap it. So I'm going to click on this chart. And I'm just going to move that over to the triangular. And I move this over the triangular. And voila! I've got my answer. I'll take this chart, copy it, bring it back here to PM, or to my model, and I'll put it right over here. I don't even need this chart again, I can delete that one. So this chart here is comparing the normal and triangular. Now, in this particular case, I give the triangular a most likely equal to the mean of the normal, and I've specified 2.5 times the standard deviations, down and up. And when I do that, you can see that the triangular and the normal are almost identical. And let's see, I want to try this. I want to say set the seed here equal to the normal. Let's go up to the normal seed. Well, there's the seed of the normal. I don't think this is going to make much difference. I think they're pretty close because we're running 10,000 simulations. So you can see they're very close. Now, dynamically, if I come in here and I change this, let's say to a 1, well, now they're going to be different. But look how quickly I can see how that distribution changes for the triangular. The normal didn't change at all. Or I could go up here to 8, and we see a different answer. Now, it's repeatable. I can put 3 back in here, and I'm right back to where I was. Okay, I think I'm going to stop here. I hope you got value out of this seminar. And if you did, I would like you to consider a contribution to probability management, tax deductible, of $10, $25, $50, or if you can afford more, that would be great. And if you want more information, go to probabilitymanagement.org. You can attend one of the live webinars. You can download the SIPmath toolbar from Probability Management website, and if you need assistance in installing it in Excel, there is a video on how to quote, install SIPmath toolbar. Just search on that. And then you could also check out my YouTube channel, Brian Putt. So thank you very much.